Our goal is simple. We want to take the CO2 out of the atmosphere. So we are a student team. It's a team composed of around 30 students from all disciplines and all sections. And we're building together a big machine that will be on campus in Lausanne and will start taking CO2 out of the atmosphere around the campus.
Chacune des colonnes va absorber et désorber du CO2. Cependant, quand on fait fonctionner la machine, ces 3 colonnes vont faire ce travail en alternance. Par exemple, 2 colonnes vont absorber du CO2 en faisant passer de l'air dedans, tandis qu'une autre sera chauffée pour libérer le CO2.
Dans la Carbon Team, moi, mon rôle, c'est de m'occuper de trouver un système pour chauffer les adsorbants. Il faut chauffer les adsorbants pour libérer les molécules de CO2. Il faut essayer de faire un système qui utilise le moins d'énergie possible. Sinon, ça ne sert à rien d'avoir une machine qui consomme énormément de CO2, du coup qui libère du CO2 pour capter du CO2, etc. Du coup, j'ai étudié environ une quinzaine de configurations différentes pour trouver une qui était la plus optimale. On a utilisé les fils à 100 degrés parce qu'on a trouvé que pour notre système, c'était la température optimale entre le coût, libération des molécules de CO2 et consommation d'énergie.
So we're working with 7 laboratories at EPFL, and each one of them is developing one piece of the puzzle, and we're just taking them together and sticking them in one big machine that will be able to capture the CO2. We're working with Prof. Queen's laboratory that develop adsorbents. You can imagine them as powders, and it works like a sponge.
Effectively, what my lab is focused on is the design of porous materials. And so within the context of the Carbon Team, effectively what we're doing, we're working with them to design porous materials that can effectively capture carbon dioxide directly from the air. The materials that we're designing, we kind of decorate the insides of the materials inside the pores so that they can really capture large quantities of carbon dioxide at very low concentrations, which is, air, it's around 400 to 420 parts per million. And so our adsorbents can capture it at such low concentrations.
In parallel, we're working with Prof. Agraval's laboratory that is developing graphene membranes that acts like a tray. So imagine you're at home doing pasta, then you put your pasta with water in this tray, and then you have the only water coming out. So same concept, you have the air coming in, and you have these small holes that only lets the CO2 go out.
So the membrane is based on an atom-thick layer where we incorporate by chemistry small holes. So we are exploiting the fact that CO2 is the smaller molecule, and so it's like a sieve, like as you have in the coffee filter.
And so we're effectively testing our adsorbents for carbon capture. We're also testing the membranes for carbon capture and then combinations thereof. And the idea is that by doing this, we can effectively decrease the cost significantly of the carbon capture-based process.
Capter le carbone est très important et peut permettre de répondre à plein de problèmes du 21e siècle, comme le réchauffement climatique.
At first, of course, it will be really small quantities. We'll be capturing minuscule quantities of CO2. So we hope to afterwards have a bigger prototype, then a bigger prototype, and capture bigger quantities of CO2.